Hi, this video will cover section 2.4, complex numbers. The objectives for this section will be to use the imaginary unit I to write complex numbers, also to add, subtract, and multiply complex numbers. And to divide, we're going to use the concept of a complex conjugate. And that way we will be able to write the quotient of two complex numbers in standard form. And the fourth one will be to find complex solutions of quadratic equations. So the imaginary unit I is the solution to the quadratic equation that you see here. So if we were to solve for x, we will have x squared is equal to -1. And to undo the square, we know we have to take the square root. And so we will have x by itself on the left side and the right side. If you were to enter this in calculator, you will get an error or perhaps a message saying no real solution. And the reason for that is that there is no number that when you multiply it, for example, if you multiply 2 times 2, or if you're squaring 2, you will get 4. But if you also square -2, because of the double negatives, the answer will still be positive. So to find the square root of 4, for example, it could be +2 or it could be -2. But if 4 was negative, then that wouldn't be equal to a real number. So we say no real solution. So what we're going to do with the imaginary unit I, and so by the way, it is defined as the square root of -1. So here we could say plus minus the square root of -1, but that will also be x is equal to the positive or -1i, like that. So remember that is equal by definition to -1. And so the way we use this is, for example, continuing with this problem, the -4 could be factored with a -1 times 4. And so if we take this product inside the square root and break it into two square roots multiplying each other, you could see how the square root of -1 is going to be equal to I, and the square root of 4 is 2. And so, of course, we could also say the positive and the negative 2i. Some cases we only use the principal square root, which will be the positive square root, and when in others we will use both the positive and the negative solution. So if we use by definition that the imaginary unit I is equal to the square root of -1, then if we were to square both sides, we will have I square, and then on the right side of the equal sign, the square root and the square will cancel each other out. And so the answer will just be what's inside the radical -1. So that's why we say I square is equal to -1. That's also an imaginary unit of I. So complex numbers, let's go back a little bit. So we have that's the title of our section, and so I want to make it clear that complex numbers is the big set of numbers, and everything that we have been doing is in the set of real numbers. So real numbers are also complex numbers. It just happens that the imaginary part is equal to 0. So a complex number in standard form is defined to be like this: a plus bi. And the first part, a, that's the real part, and the second part is the imaginary part. So ba and b here are just numbers, and so the fact that it has the I in next to the b, which will be like a coefficient, that tells us that it is the imaginary part. So those numbers, we call them imaginary numbers. So they are a subset of complex numbers. And we have some that will have, for example, 2 plus 3i. That is an example of an imaginary number. And we could also have something like just 4i, for example. But in standard form, what that will be equal to is 0 for the real part and then 4i for the imaginary part. So this type of numbers are called pure imaginary when the real part is 0. And then with real numbers, what happens there is, for example, -4. That is a real number. And the imaginary part, it just happens to be 0. So this is just equal to -4. And the standard form, we always write the real part first and then the imaginary part. So imagine that complex numbers is, I don't know, your mom, and then you are the real, the set of real numbers, and then one of your siblings, if you have any, is the set of imaginary numbers. Okay, so now going back to here, we have what I was mentioning, the standard form. It is always going to be a plus bi. You all know how a WebAssign could be. So if you have an answer and it says enter your answer in standard form, if you were to enter something like this, for example, 2i over 3, it will count it wrong. So, or even if you were to enter it 2/3 of I plus 5, it will count it wrong because of the order. And this one it will count it wrong because you're not separating the coefficient that goes next to I. So the correct way in standard form will be to write the real part first, and then the number that goes next to I, write it by itself, and then I next to it, multiplying that number. So here we have an example. So let's see why it is equivalent to that. So if we take this number, it will be -5. And then I am going to factor the square root of 9 as the product of -1 times 9. And then I'm going to take the square root, or I'm going to rewrite it with each square root there as a product of the two square roots. So from here we got -5. We know the square root of 9 is going to be 3 or -3, but for this one we will only take the principal square root. So it will be +3, and then the square root of -1, by definition, remember, the square root of -1 is I. So that will be the answer, -5 plus 3i. Now, one of the objectives is be able to use the complex conjugate. So we'll go over this in a minute, but I just want to point out that the complex conjugate of this number will be the same digits, and the only difference is that that plus is a minus, so it will be the opposite sign. It kind of comes from the fact that the square root of 9, it could be plus or minus 3. And so the square root of -9, if we use both square roots, it will be plus 3i, but it could also be minus 3i. So that's good to know, but we will review it in a minute. These two are called complex conjugates. So we have the definition of a complex number, formal definition. So we have let A and B equal to real numbers. So the number A plus BI is called the complex number. It's called a complex number, and it is said to be written in standard form. The real number A is called the real part, and the real number B is called the imaginary part of the complex number. So if B equals to 0, when B equals to 0, the number A plus BI is a real number, as I showed you before. And when B does not equal 0, that means that we have the imaginary part attached to the real part. And then finally we have in the form BI, if A was to be 0, and so those numbers, we call them pure imaginary. So remember, A plus BI, standard form. We have real numbers, and this is when B is equal to 0. And here we have the imaginary. And this is when B does not equal to 0. Okay, and then a subset of those will also be when B, not B, but A equals to 0. So then we will call that pure imaginary. Such as, let's say, 3i. That's a good example. Okay, and another example here, we could have, I don't know, -1 minus I. That's another example. And then real numbers, of course, you guys don't need any, but I'll write some here. All of those are real numbers. Okay, so moving on. Now we're gonna go over how to add and subtract the numbers. So before that, if we have this statement here, the equality of complex numbers. So if you have two complex numbers and they're both in standard form, and then you're saying that they equal each other, like we have here in that equation. So that means that the real parts, this can only happen if the real parts are equal, but also the imaginary part. In this case, we're using the letters B and D. So if those are equal, the real parts must be equal, the imaginary parts must be equal, and that is the only way we could guarantee there's equality between the two numbers. Now for addition and subtraction, it's very easy. We are going to put the real parts together, just like if we were combining like terms, and then we will be adding the imaginary parts as well, and then we will of course keep them with the imaginary unit I. So for a difference, the trickiest part will be that that you remember to distribute the negative to both the real part, so we have -c here, and to the imaginary part, -d. And it is the same thing. In this case, we will subtract the imaginary parts, we subtract the real parts, And just like if you were combining like terms. So you'll see how easy it is. So I'm gonna first rewrite it without the parentheses. So it will just be 4 plus 7i and plus 1 minus 6i. Then I'm gonna group the like terms. So we are gonna put the real parts together, 4 plus 1. And then we're going to group the imaginary parts, 7i minus 6i. And we say minus because that's just the sign that it has in front of it. So to finish this, we will combine like terms. So 4 plus 1 is 5. And then from here, 7i minus 6i, it will be positive 1i, so it could just be that, and that is in standard form. Real part first, imaginary part second. Now, next problem, it will be 1 plus 2i by removing the parentheses, plus 3 minus 2i. And then we're going to have combine the real parts. 1 plus 3 is 4. And then 2i minus 2i is just equal to 0i. And if you have to enter your answer in standard form, keep in mind that you might have to include the plus 0i. If you just enter 4, the real number, and then you get it wrong, just try entering 0i. Okay, next we're gonna combine some we're gonna be performing subtraction of complex numbers. So what I'm going to do is rewrite everything by getting rid of the parentheses. So let's do that. We start from left to right. So 3i. Then we're going to distribute the negative, like I said. So it will be negative 1 times 2, negative 2. So it will be plus 2. Then we will distribute the negative sign to the plus 3i. And that will give me minus 3i. Then we move to the next negative, and we need to distribute that as well. So that will give us minus 2 minus 5i. Now we're going to combine like terms. So you can see here how 3i minus 3i, they cancel, is equal to 0. And then we have 2 minus 2, so that's 0 as well. So the only thing we have left is negative 5i. However, in standard form, you might have to enter 0 minus 5i. Okay, next one, we have a combination of addition and subtraction here. So let's clear the parentheses first. 3 plus 2i. Then here we have a plus, so we could just clear parentheses without distributing anything or changing the signs of anything. So plus 4 minus I, just the same as inside the parentheses. Then we distribute the negative here and here, and we will get minus 7 minus I. Now let's combine like terms. So the real parts first. We have 3 plus 4, that is equal to 7, and then we have here a minus 7. Then we have 2i minus I minus I, so that will be plus 2i. Let's combine the two negative ones here and here, so that will be minus 2i. Now you can see how this expression will just turn into 0. So we have 0 for the real part and then 0 for the imaginary part. So if you enter 0 for your answer and it counts it wrong, perhaps you might have to enter it in standard form like that. It's just how WebAssign works. Okay, next we're going to move on to multiplication. So first we're going to use the distributive property. So here 4 times negative 2 will be negative 8. Then 4 times 3i will be positive 12i. And that's it. That's all we have to do. Now, with the next problem, we have two terms in each set of parentheses. So what I'm going to do is distribute the 2. So it will be 2 times 4 plus 3i. And then I'm going to distribute the negative I. So it will be minus I times what we have in this parentheses, 4 plus 3I. That is the distributive property. So we will get here 2 times 4 is 8. 2 times 3I is 6I. Here, negative I times 4 is negative 4I. And then negative I times 3I is negative 3I squared. And so here, we're going to make a little change from the first slides. We had the definition that I is equal to the square root of negative 1, but we also had the one for I squared. So anytime we see I squared, we're going to replace that with the number negative 1. So if we continue going, we have 8. Let's combine the like terms here. So 6I minus 4I will be 2I. And then here we're going to have negative 3. We replace that I squared with the number negative 1, just like that. Then we keep simplifying 8 plus 2I. And you know that we are going to have a double negative here, so that will turn that into a positive 3. And finally, we combine like terms. So 8 plus 3 is 11. And then we have plus 2I. And that will be the final answer. So here I use the distributor property, but if you want to, I don't know if you like to use the FOIL method, like if you were multiplying two binomials, you are, of course, free to do so. So it will be like first terms, 2 times 4, and then outer terms, 2 times 3i, and then the inner terms, negative I times 4, and then the last term. So it will be like the negative I times 3i. So that's another way to obtain the product. Okay, so we're going to do the same here, and why don't we just do it that way? So first, so 3 times 3. I'm going to write it like the long way. And then outers, so it will be plus 3 times 2i. And then the inner terms right here, plus 2i times 3. And then finally, the last term from each binomial. So 2i times negative 2i. So plus 2i times negative 2i. Okay, so let's see what will happen here. So 3 times 3 is 9. Then we have the 3 times 2i is 6i. And then we're going to have, hold on, I feel like I'm missing something here. Okay, yes, this should be negative right here. Because it was 3 times negative 2i, so then here this one should be negative 6i. Then from here we're going to get positive 6i. And then from over here we're going to get negative 4i squared. So you can see clearly here those two will cancel, they're opposites. So we're going to have positive 9 minus 4, and then we'll have to replace that I squared with negative 1. Remember, every time you see 1. And so now we're going to have 9 plus 4, which is 15. And you could see that we went from the product of two complex numbers to a result that is just a real number. So the reason for that is that we multiply two numbers that happen to be complex conjugates. As you can see, they have the same numbers absolute value, but we have the imaginary part, they're opposites. So plus 2i, negative 2i. That is how you know that you have complex conjugates. And they always come in pairs. That's why we call them that too. Okay. So we will go back to more examples of complex conjugates, and then I will show you a trick so that you don't have to do all this like the long way. Okay, so here we're going to square a binomial. So remember that squaring a binomial, you don't just square the real and the imaginary part. You have to actually carry out the multiplication. You end up with 4 terms, and then you'll be able to combine some. So if we multiply 3 times 3, and then we will multiply 3 times 2i, positive, and then we will multiply 2i times 3, and then finally 2i times 2i. And here everything's positive, so it's kind of nice. All right, so 3 times 3 is 9, and then plus 6i, plus 6i again from here. And then here we're going to get plus 4i squared. Now remember, we have to do that substitution, but let's combine the like terms here. So 9 plus 12i, and then this will be 4 times negative 1. So again, we replace I squared with negative 1. So that is going to change the sign of the 4. So we're going to have now minus 4. And then, of course, we combine like terms. So the real parts, 9 minus 4. And that will give me 5. And then we write the imaginary part second, plus 12i. And that will be in standard form. Okay, so let's see what's going to be our shortcut for complex conjugates. So again, you could see that we have the same for the real and imaginary part. The only difference is the sign of the imaginary part, right? So if we multiply them by the long way, so a times a, it will be a times a, and then a times negative bi, and then we will have positive bi times a, and then finally positive bi times negative bi. Okay, so we will get a square. Here we're going to get negative abi, and then from here we're going to get positive abi, and then here we're going to get negative b times b will be b squared, and then I times I is I squared, like that. You could see that 2 terms in the middle are opposite, so they cancel each other, they equal 0, and now we have a squared minus b squared, and then the I squared will be replaced with negative 1. So now this will be a squared, negative times a negative will give me positive, so positive b squared. That is going to be the case every time we multiply 2 complex conjugates, such as the example that we have here. And again, how do we know they're complex conjugates? Because the sign of the imaginary part will always be the opposite from the other. Okay, so let's do an example of using this shortcut. So for example, if I have 4 minus 2, let's use 3, minus 3i. The complex conjugate, The complex conjugate of that will be 4. Since here we have a minus, the conjugate will have a plus. So the shortcut for this is going to be to take the 4, which is here like the A, and then we're going to square it. Then we're going to add, we're going to take the coefficient of the imaginary part, the 3, and we're going to square it. And here we don't really care if it's a positive 3 or a negative 3, because once we square it, we're going to get the same number, which is 9. 3 times 3 is 9. Negative 3 times negative 3 is also 9. So then we get 4 squared is 16. 3 squared is 9. So that will equal to 25. So let's go back to the one that we did previously, that we did it the long way. Right here. So let's see if our shortcut works, and we also get 15. So we have 3 plus 2i times 3 minus 2i. If we multiply, it will be 3 squared plus 2 squared. So that will be 9 plus 4. Oh my gosh, I just realized something. That is equal to 13. Oh no, how embarrassing. So I'm sorry, this should have been not 15, 13. I apologize for that, but yes, we do get the same 9 plus 4, 13. 9 plus 4, 13, not 15. So yeah, this is a pretty cool shortcut. You square the 3, you square the 2, and you add them, and that's it. And how do we know that it will just be real? Because you could see here that the two terms in the middle will cancel each other out because they have opposite signs. So anytime you can use the shortcut, I will recommend that you do so. All right, so now our next basic operation, we already went over addition, subtraction, multiplication. So now we have division. So here the quotient, so it's implying that we'll be dividing. So we are dividing the number 2 plus 3i by 4 minus 2i. So the way we're going to divide this is by multiplying that fraction by the complex conjugate of the divisor, the denominator. So if that has a minus, then our complex conjugate will have a plus. Now, because we don't want to change the expression, we just want to write it different, in a different way after dividing, then we need to make sure that we're only multiplying by 1. So we do whatever we do to the bottom, we're going to do to the top as well, because if you look at this fraction here, it's just equal to 1, just the fraction, not the whole division. But that fraction is equal to 1, and that's why we do that. We multiply top and bottom. You must. Okay, so for the bottom part, we're going to be using the shortcut. So that's going to be 4 squared plus 2 squared. We could use the shortcut because they are complex conjugates. And now we need to multiply times the numerator. So in this case, we're going to have 2 times 4. Oh, did it again. Okay, 2 times 4, which is 8. And then we will multiply 2 times positive 2i, so that will be 4i. Then we will multiply 3i times 4, so that will be 12i. And then 3i times 2i, that will be plus 6i squared. And of course, we need to replace our I squared with a negative 1. So from here, we're going to get 8 plus, let's combine the two terms here in the middle, the 4 I plus 12i, so that's 16i. And then we have the plus 6 times negative 1. Okay, for the denominator, we have 4 squared, that's 16. 2 squared is 4. And please don't add the numbers before you square them. Okay, so now we have 8 plus 16i minus 6 over 16 plus 4 is 20. Now we can combine the real parts. 8 minus 6 is equal to 2 plus 16i over 20. Now, that is not it's the correct answer, but not in standard form. So we need to split the fraction, so the 20 divides the real part, but also the imaginary part. Okay, and we could simplify each fraction. So the real part we can divide by 2, top and bottom, so we will get 1 over 10. And then for the imaginary part, we can also divide, let's divide by 4. 16 divided by 4 is 4. So 4i over 20 divided by 4 is 5. Now, if I enter this on WebAssign, it will count it wrong. Why? Because we have the letter I, the imaginary unit, here with the coefficient. So we need to separate those. So in standard form, it should be 1 over 10 plus 4 over 5, and then I over here by itself. Next to it, indicating that there's still multiplying. And that's it. That will be the answer for that problem. Okay, so complex solutions of quadratic equations. So this is one of those where we will only use the principal square root, and that will be the positive square root. So like here, for example, so if we were to be asked to find the square root of -3, you could see how they factor 3 times -1. Then that product inside the square root was written as the product of 2 square roots. Square root of 3 times the square root of -1. Now, square root of 3 is, we cannot just get an integer, so this will be the exact answer. You just leave it in radical form. And the square root of -1 by definition is just the imaginary unit I. So here, instead of saying plus minus square root of 3i, we just take the principal square root, which will be the positive 3i. And so that's the same thing that we have here, the positive square root. All right, so we're gonna do our, I believe this is the last problem, but let me give you guys an example of this. Let's say that you have the square root of -25, and you have to find that. So in this case, you could factor as -1 times 25, and then break it into the square root of -1 times the square root of 25. So the square root of 25 is positive or -5, and then the square root of -1 is I. However, we just want the principal square root, and so we are just going to keep the one with the positive sign, so it will just be 5i. There might be some problems in the homework that require a little bit more thinking, so please make sure that you don't get stuck for too long. Send me a message or reach out to the online tutoring. Okay, here, how would we apply imaginary numbers to solving a quadratic equation? And so remember, to solve something is to find the solution. or solutions, I should say. And so those solutions will be those
7:48 p.m.
So that was my watch. So those solutions are those x values for which the y value is equal to 0. And that's what we're looking for. We're looking for two of those. Now, since we're in the imaginary or complex numbers section, I can tell you that the two solutions that we will get will be imaginary numbers. So let's see. Just so you know, we need the quadratic formula, which is negative b plus minus the square root of b squared minus 4ac, and then everything divided by 2a. So right here, I like to look at the coefficients, and I like to write them on the side. So for example, we see that a is equal to 3, b is the coefficient of x, so it's negative 2, and then c is the constant term. So then after that, I go ahead and substitute everything into the formula. So for example, here, negative b, I have a negative 2 for b, but the formula already has a negative in there. So that's why I like to write them down so that I don't overlook any negative numbers. I don't like to just say A, B, C. No, I don't like that. Okay, and then the formula has the plus minus square root, and then we see b squared. So you can see how they're keeping it inside parentheses. That's very important because you have to get a positive number out of there. Then the formula continues with another negative. You could see that here. And then we have 4 times a. So a is a 3 right here. And c is a positive 5. So you could see that there. And then the formula has that over 2a. And you could see everything is over 2a. A is equal to 3. So that's where we substitute there. And then we're going to simplify it now. So first, from left to right, we have here this double negative. So that will be positive 2. Plus minus. The square of negative 2 is positive 4. And then we will have negative 4 times 3 is 12, times 5 is 60. Yes, and then over 6. So now we have 2 plus minus 4 minus 60 is 56 over 6. Oh, and this should be negative because the negative 60 has a bigger absolute value. Oh, so it will be negative 56. Okay, now for negative 56, we're going to factor it. So first we need that negative 1. And then we could factor it by using two numbers where one of them is a perfect square. So for example, 56 could be divided by 4. Yeah, so let's do that. So it will be times 4 and times 14. There we go. So we take the square root of, well, negative 1 will be I. And then the square root of 4 is 2. And then the square root of 14, we're just going to leave that inside the radical. Okay, and let's remember everything is divided by 6. So what this means is that the 6 divides the real part. And of course, you could see this is one of those cases with the quadratic formula where you do use both of the square roots. the positive 2i and the negative 2i times the square root of 14, of course. Okay, so plus minus 2 over 6 square root of 14 times I. And now here we're going to reduce or simplify the fractions. So for the 2 over 6, that is 1 over 3. And then we have plus minus. And then here, 2 over 6 is also 1 over 3. And then we have that times the square root of 14. So in reality, we could just write the square root of 14 there in the numerator, because 2 divided by 2 is a 1. So it's like you have that invisible 1 here, which we don't really need. And then we still need the imaginary unit I. So those are the solutions to the equation. In fact, we have 2 of them. One of them is 1/3 plus the square root of 14 over 3i. And the other one, I'm calling them x sub 1 and x sub 2, it will be 1/3 minus the square root of 14 over 3 and then the imaginary unit. And yes, you could see how they are complex conjugates. And yeah, like I said, they always come in pairs. So this is the end of the video.